Module for video C, we're talking about dishes and tree hyperparameters. So in the last video, we made this vastly overgrown decision tree, so big we can't really even see it, by running dishes and tree regressor and only specifying the random state, not specifying any other variables. So now we're going to look at the other conditions we can give our decision tree in order to control its growth a bit. So the first one we're going to look at is max depth. So max depth sets how deep or how many layers down the tree can grow. If we go up to the very first decision tree we looked at, this little guy here, the max depth of this decision tree was 2. So just one layer here, and then the leaf nodes. So that's what max depth is, and by restricting the max depth, you obviously restrict how big the decision tree can grow. But that's not the only thing that you can restrict if you're trying to control your decision tree. We also have min sample split. So this is the minimum number of samples that must be in a node for the tree to even consider splitting on that node. So if we look a ways up into this tree at a random node, we saw that, okay, right here, there were 14 samples in this node, and then it kept splitting for quite a ways down. Another way to restrict the growth of the tree is to say, okay, well, if, for example, we get to a node and there's only 5 samples in that node, let's just stop there. Let's not try to split it out. More specifically than that, I'm not interested in having leaf nodes with, less than this certain amount in them. So that's what the min sample split is. And then there's also min samples leaves. So this is the minimum of number of samples that can be put into a new node, which might sound like, well, isn't that kind of getting at the same thing as min sample split? Similar, but for example, if your min sample split was 10 and your min sample leaf was 3, you could have a node that had 10, and based on the min sample split, you would be able to split that node. You could maybe split it into 5 and 5, but if the way the model wanted to split it was actually into 2 and 8, then it couldn't do that because that would violate the min sample leaf. So these are the hyperparameters that we want to look at. Now, we could just look through and decide, okay, this is what I want each of them to be and run the decision tree. However, what we'd like to do is do a bit of optimization and actually see which set of hyperparameters is going to give us the best decision tree, and the best here being what will give the best predictions on new data. Of course, if we're just predicting the data onto itself, the more overgrown the tree is, the better it's going to do. But when it comes to predicting onto new data, we often find that decision trees that aren't too complex do better at generalizing new data because they aren't too specifically focused on the test data. So the way that we're going to do this is through a method called cross-validation. So we talked before how we've already split our data into a test set and a training set. And in the final evaluation, we will evaluate our model on the test set. However, as we're going through and trying these different hyperparameters, we don't want to be evaluating how each separate model does on the test set, because we could end up picking, if we just do that and then pick which ones does the best, we'll end up picking a model that specifically does the best on this test data set and still might not be the best model for a general test data set. So instead what we're going to do is a method called cross-validation. So how cross-validation works is each time you make your model, let's see, and I think this will be, there's a couple different ways it can work. I believe down here we're using 5-fold cross-validation. So what it will do is it will split our training data set into 5 groups, and then it will go through and it will kind of loop through 5 times, and each time it will make a model just using 4 of those groups and evaluate it on the 5th one. And it will go through and do that 5 times until it's evaluated on, it's left out and then evaluated on each of those 5 different groups, and then it will average it to give an accuracy. So yeah, let's walk through this code. So first of all, I'm going to define the set of hyperparameters I want to test. So for max depth, I want to look at max depths of 3, 5, 7, and 9. For the min sample split, I'm going to look at 2, 5, 10, 20, and 30. And then min sample leaf, I'm going to look at 1, 2, and 5. You might say, well, where did you pull these numbers from? A bit of this is experience and knowing, how big I might want my final tree to be. And then there was also a bit of trial and error. I ran this code a couple times until I kind of figured out what were good ranges to put these in. So I've defined what I'm going to search over. And then here I'm setting up my loop. So I've defined a variable called best score and best parameters. So initially I say that my best score is infinity and I don't have anything in my best parameters, but as we go through you'll see that I'm going to end up storing in this variable what the best score and what the best parameters end up being. So then we do a simple nested for loop. So for depth in max depth, for split in min split, and for leaf in min samples leaf, we go through and we make our model using those parameters. Then right here we perform that cross-validation, and then we're going to print out, hey, these were the parameters we used, this was the cross-validation accuracy that we achieved, and then we're also going to keep track of the best model. So that's what we do right here. We say, okay, if the mean score that we achieved was less than what we have logged as our best score, then let's keep that best score and update what our best parameters are. So let's go ahead and run this. Now, since our data set is pretty small, this ran really quickly. It only took 2 seconds to go through quite a few different models and quite a bit of cross-validation. If you're working with a really big data set, this can be a very lengthy process, and you might find that you need to train over less hyperparameters, or go to a GPU accelerator, or just wait for a really long time. Luckily, this data set is really small. So if we scroll through here, we can see all of the different models that it tried. And for each model, it tried the different things, and then it achieved a different cross-validated accuracy. And actually, there's a ... right here. I can expand it. Come on, why aren't you expanding? There we go. And we can see, yeah, it went through quite a few. But if we go down to the very bottom, we have our best ones. So the best parameters found were when the max depth was 7, when min sample split was 20, and when the min samples in a leaf was 2. That's what got the best cross-validated accuracy. So we've identified the hyperparameters we'd like to use. Now we're going to create our final model. And so far we've just been doing all of this on the training data set, so we'll create our final model and then we'll finally test it on the test data set and see how we did. So let's do that. So there we go. We have achieved a final mean squared error of 17.46. If we think back to our linear regression model, we had a mean squared error of 19.3. So we have achieved just a little better accuracy. And then also let's actually take a look at this. So this is our decision tree. Yeah. Let's scroll over here. And there we go. So this is how it goes out. It starts at RM, makes some other splits. It looks like LSTAT and RM are common variables to split at. And it splits down until we get to our leaf nodes. So depending on your application, you might look at this decision tree and you might be like, yep, I'm really pleased with this decision tree. It gets me good accuracy, and this is a good level of complexity. For other applications, you might look at this level of complexity and be like, you know what, this is honestly too much. You know, if you're going to try to be presenting this model to a really general audience, this might be a lot for people to take in. However, all in all, I'm pretty satisfied with this. To me, this is a good level of complexity. We've got a good test error, but you can still look through this model and follow the logic and see what's going on there. So yeah, thanks for joining along. This has been Decision Trees, and have fun making decision trees of your own.